These are the solutions to question number 4 from the 2014 examination paper. Question 4a concerns a three-dimensional system. We're going to want to determine the stability of critical points. And 4b, we want to determine the fixed points of periods 1 and 2 and the stability of fixed points of period 1 for this complex map. So for 4 part A, here is our three-dimensional system. So to find the critical points, we want to solve x dot equals y dot equals z dot equals 0. So we can use the solve command in MATLAB, and you'll see you get 3 critical points. So these are the 3 critical points. The Jacobian is dp dx dp dy dp dz, dq dx dq dy dq dz, and dr dx dr dy dr dz, where x dot is p, y dot is q, and z dot is r. And simple partial differentiation gives us this Jacobian matrix here. To find the stability of these 3 critical points, we just substitute for x, y, and z into the Jacobian matrix. So for the first critical point, J is equal to this matrix. Again, we can use vect_val to find the eigenvalues and eigenvectors for this matrix, and here are the eigenvalues. So the eigenvalues here are 0.38367i, minus 0.367i, and minus 1. In this case, because the real part of some of the eigenvalues is 0, this is a non-hyperbolic critical point, so we can't say whether it's stable or unstable. For the next critical point, here is the Jacobian. Again, we can find the eigenvalues of this easily with MATLAB, so here are the eigenvalues, and you can see for 2 of the eigenvalues the real part is positive, so this is an unstable critical point. And for the final critical point, here is the Jacobian matrix. We can find the eigenvalues of this Jacobian, and again 2 of the eigenvalues have positive real part, so again this is an unstable critical point. In order for a critical point to be stable, all 3 eigenvalues would have to have negative real part in order for the critical point to be stable. For part B, we have this simple complex iterative map. To find fixed points of period 1, we want to know when does Zn plus 1 equals Zn equals Z, say, and that gives us this simple quadratic equation, which again we can solve with MATLAB. So if you solve this with MATLAB, here are the 2 fixed points of period 1. To determine the stability, we differentiate f. Here is our function f. We differentiate this with respect to z, and you can see we just get 2z, because you differentiate constant, you get 0. So the derivative is 2z, and then we want the modulus of this df by dz. If the modulus of the critical point if the modulus of the gradient is less than 1, the fixed point is stable, and if the modulus is bigger than 1, the fixed point is unstable. So you can see for the fixed point z11, if you take the absolute value in MATLAB, you take the absolute value of 2 times this complex number, then we get this number which is bigger than 1, so z11 is unstable. Similarly, twice z12, so if you do twice times this number and then take the absolute value, we get this number which is again bigger than 1, so z12 is also unstable. To find fixed points of period 2, we want to know when does Zn plus 2 equal Zn equals Z. So that gives us this expression here. So Zn plus 2 equals Zn squared plus 1 plus 2i squared plus 1 plus 2i. We just replace Zn plus 2 and Zn both with Z, and that will give us a quartic equation which you can solve in MATLAB. 2 of the roots should be the same as these 2, and here are the other 2 roots. So when you solve this quartic, we get 4 roots, 2 of them are period 1, and these are the fixed points of period 2. So again, we can use the MATLAB solve command to solve this quartic equation. And you can check this yourselves using MATLAB. And that concludes the solutions to question number 4.